Welcome back. So I did two things. I posted all of the examples we went through together on Tuesday. I posted all of those as part of the slide deck for the lecture. They're all on the website now. And there's also the video recording. It's on YouTube. You can find a link on the website, etc. And the other thing I did is I looked at the calendar for the rest of the semester, and I proposed two dates for the final report deadline and for a first milestone, a milestone towards that, coming up right before Thanksgiving, November 22nd, proposed milestone deadline date. Okay, so what we would like to do, Hongbo and I, is ask you to write the introductions to your final reports and thorough lit reviews. Hopefully, we've given you some useful feedback the first time you wrote the lit review for a homework assignment. This time you're doing it for real for your actual projects. And submit all of these intro and lit review by the 22nd. We'll get a chance to give you some more feedback on that. A few points. It's mostly for us to give you some feedback. It's not worth a lot of points. And then the final reports are going to be due on the 12th, I think, of December. So that's the first week of exams. That gives us about a week to grade them and whatnot before the grades are due. And I don't know, we're all off for winter break or something. Okay, so that's the plan. We'll have final presentations before then on the last week of class. Tuesdays and Thursdays will be short final presentations. We'll go through everybody. We'll do a similar thing as we did before with kickoffs, shared slide deck, all of that. We'll give each other comments on the deck like we did before. And you'll have a few days after your final presentations to incorporate whatever feedback you might get until you're supposed to submit the final reports the Tuesday thereafter. Okay, that makes sense? So presentations will be the final week of class, and then report will be the week thereafter. It's the first week of exams, but we don't have an actual exam. Okay. I want to remind you that we actually care about these. This was the most important. I mean, we care about everything, but we care especially about these. This is the most important, homework assignment project. The reason why you're taking this class is hopefully to show off all of these cool things you've learned about designing and carrying out rigorous empirical methods, mixed methods research studies. And we treat these reports very seriously. We expect that the writing quality would be, publishable. Even if the work is not ready, we expect that the writing and the thought that goes into this is really, thorough and careful and polished. So that's the plan. Okay, so any questions or thoughts on administrative things?
This is a minor question. Is there any specific template you want us to use, or can we just use like an ACM?
Yeah, I don't care what you format it as. Use whatever makes sense. Maybe if you already have a venue in mind that you're writing for, use the template of the venue you're writing for. I don't care what it looks like. You could make up your own, or you could take one of the standard conference templates from, I don't know, the venues we typically publish at. Whatever makes sense. I don't care what the format is. We care about content, not format. Okay. Okay. So what I'd like to do today is three things, hopefully. One is just to finish off this example of Simpson's paradox. This is one of the most amazing things that can happen in quantitative data analysis or statistics. And I want you to be well aware of this and to have understood the example. And then we're going to go and do the presentations. Hopefully the third person has signed up in the meantime. Last I checked, there were only 2 people signed up for presentations of the 3 papers we proposed. I was hoping that there would be volunteers for all of them. I haven't checked recently. Oh, I actually do. I have it in front of me. There's one missing. So please, this is part of the work that you're expected to do for this class. So please sign up and present these when we put them up for presentations. We have one, we're short one, but that's okay. The third thing I want to do, Aiden, yes.
Sorry, quick how many these presentations supposed still have sometimes like either taking down.
Usually they're pretty short. We want to focus on summarizing the main points of the paper and zooming in on the particular method that we're discussing. In this case, the regression modeling framework for analysis, and focusing and discussing that in a little bit more depth. Maybe seeing if there's any good things about it, any bad things about it, that sort of thing.
So in 5-ish minutes.
Sure, 5-10 minutes. That's okay. The third thing I want to do is I want you all, so thank you for bringing computers. I want you all to actually play hands-on with the data set. So I have a small in-class activity that we could start to do, hopefully finish in class. If not, you could finish afterwards. But that's the plan. Right. So I want to come back to this example that I left off with on Tuesday. This was on the y-axis, the number of errors people make while typing, and on the y-axis, the speed with which they're typing. And the intuition would be that the faster you type, the more errors you make, because it's just hard to keep up with the increasing speed of typing. Yet, if you look at this data set, it shows exactly the opposite effect of what you might expect intuitively. You see that the faster the speed, the fewer the number of errors, the lower the number of errors, which is very counterintuitive. And then I showed you that this is an aggregation effect because the data came from, say, in this example, 5 different people that were typing different documents. And if you were to look at the population overall without taking that into account, you would see that there's this decreasing trend between speed and a number of errors. But if you actually zoom in on each participant individually, you will see the exact opposite effect, namely that for every person, the faster they type, the more errors they make. But at the same time, people that happen to type faster, maybe they're more experienced with typing, they make fewer errors overall. So this is an example of ecological fallacy. You'll hear this term used many times, maybe. It's a very common type of error that occurs with statistics or data analysis, ecological fallacy, because depending on which level of aggregation you're looking, if you're looking at the individual person versus if you're looking at the population as a whole, you're seeing opposite effects. You would draw opposite conclusions. So this is why it's called ecological fallacy, because if you look at the individual, you would conclude something opposite than if you look at the entire population. And so just to illustrate this, here's a simple linear model of the entire population without distinguishing in any way between participants. I'm modeling errors as a function of speed, a simple linear model on this data set, and you see this overall negative slope here, right? The higher the speed, the lower the number of errors, smaller the number of errors. Okay? And this is not an invalid model. Like if you would look at the diagnostics and whatnot, you would not be too unhappy with the way this looks. Okay, so now right. So how might we actually model the thing we're actually looking to observe, this positive relationship between typing speed and errors? So here's a second model where I include an additional term in the model. It's a factor that just models the participant. Okay, we call this a fixed effect for the participant. ID here is the ID of the participant in the study. So it goes from 1 to 5 or something like that. Okay. So I still model errors as a function of speed, but I have a fixed effect for participant. How do we interpret this? what do we see? What would we conclude?
Some of the participants are breathing and some of them are not. That's the same, right?
There's two things here. One is, we have a coefficient for speed, which we had before, and then we have a bunch of coefficients for these different participant factors. We talked about this a little bit on Tuesday. One of them is missing. Okay. Which one is missing and why is it missing? Does anybody remember? Yeah.
So for each of the participants, as their speed increases, the number of errors increases, but the factors listed there are offsets from participant one. So they just exclude participant one because each of these variables is an offset from them, and then that is kind of like your intercept of that participant. But each has the same slope.
That's right. So we have the coefficient for participant one, the one that's omitted, is subsumed in the intercept in this case, and these are basically offsets for the other participants relative to participant one. This was chosen arbitrarily because it's just alphabetically the first one in this list, but you can always change that. Doesn't really mean more than that. You can change that to be, you could choose a different participant as the baseline, or you could code this in an entirely different way. I sent you a reference for how you might code this differently. For example, you could code the deviation of each participant from the global mean, in which case you would have all 5 of them. You would have coefficients for all 5 of them in the model, if you do it in that way. But anyway, so this is what these are, and then you see positive relationship between speed and errors, right? The higher the speed, the more errors. Choose the individual level. So we're basically modeling, the slope of all of these lines, and they're all the same. They do not vary with participants. The slope is the same for all participants, but they have different intercepts. Okay, that's what's happening here. So now, the one other thing, as an aside, there's a class of models called mixed effects models. Everything I've shown you so far in the last couple of lectures when we talked about regression, all of these were examples of fixed effects models. There's a different class of models called mixed effects models. Mixed comes from having fixed and random effects in the models. You can read more about this. The idea is that this is a particularly powerful class of models to use when there's some sort of hierarchy or nesting present in the data. They're particularly powerful and appropriate in situations like these. So where does the nesting or hierarchy come here? It comes from the fact that we have multiple observations for the same participant. In other words, we could say that our individual measurements of speed and error are nested by participant. There's this implicit hierarchy in the data, right? Multiple observations within a participant and then multiple participants in the study. And so whenever you have a scenario like this with nesting or hierarchy, it's perfectly appropriate and often recommended to use these mixed effects models to encode, to account for this hierarchy. So what's happening here is this is a way to, you're using a different function in R. I'll show you more specifically later. Instead of LM, you're using Elmer, but that's besides the point. The way you're encoding this nesting is, for example, this. You're saying that there's a different intercept for every participant. Okay? So I'm still modeling errors as a function of speed, but my observations are nested by participant. I have a different intercept for every participant. Essentially the same way of modeling what we just modeled before. Okay. Now, too bad Bobo is not here. We would have a long argument about this. This is a very long discussion that I will not get into, but like one advantage of using mixed over fixed effects models, even though you can often achieve the same result with a fixed effects model, is that you're using fewer degrees of freedom to estimate these models. They're often more powerful with less data. Because unlike the previous scenario where I estimate a separate coefficient for each of these factors, here I do not do that. Here I just estimate the overall variance within group relative to between groups. So this is sort of a cheaper model to run when there's relatively little data. That's one argument. Okay, in any case, you could see roughly the same thing in the summary of this model. You could see roughly the same coefficient for speed, the same positive relationship. Higher speed is correlated with more errors. Okay. And you could see that there's some variance in speed, sorry, in errors in the outcome. There's some variance in the outcome within participants, and there's some leftover variance between participants. And this is a way of estimating how much that variance is. Okay. So now one more thing I want to show you. What if we want to capture both of these patterns at the same time? Like we have so far either captured this individual level pattern with these last two models, or we've captured this overall global pattern with the first model we talked about, but not both at the same time. Do you agree with that? Because I haven't shown you a model where you see both this negative relationship between speed and errors at the global level, as well as the positive relationship between speed and errors at the individual level. I haven't shown you a model that does that. Right? I've shown you a model that does, either or. I've shown you a model that does, either the overall global negative relationship or the individual level positive relationship. Both of these kinds of models I've shown you later were that, but not a model that does both. So there's a trick. This was very clever. I was very excited to learn about this. There's a trick where you can actually model both with a clever transformation of the original data. So what they do here is they decompose, and ignore the syntax for a second. They decompose these measurements of speed into two components. Okay, so for every person, note the group by ID syntax here. For every person, they compute their mean, their average speed. Remember, we have multiple observations for every participant. So, for every participant, we can compute some average speed. Okay. And whatever's left over, so we call that, speed mean. Whatever's left over, we call that speed, say, error, is the difference relative to the individual level mean. It's sort of like a z-score transformation. We talked about this a little before, like mean 0, standard deviation 1. It's a little bit like that. Okay, so it's mean centering. So everybody has, instead of your, do we have a, let's see. Yes, here. So this is a bit of the transformed data. So the speed column are the original values we measured. And note how the mean, this column here, the mean is obviously always the same across all of the rows corresponding to the same participant. And we have this, error term, whatever's left over, between the individual observations, right, for those documents or whatever, relative to the participants' mean. I haven't done anything else but decompose the original data. I've thrown it a little bit. I haven't changed anything else. So now, if I model, instead of having one overall speed term, I model both of these separately. And you could do this with a mixed effects model, nesting by participants. You could do this with a fixed effects model, etc. It's not relevant for this discussion. The point is, if I model both of these separately, I now get both of the effects that I observed visually in the original data. I see this overall positive correlation between speed and errors at the individual level, and I see the global negative relationship between experience and errors. Like people that type faster overall make fewer errors on average because probably they are more experienced typists. You will also probably complain, but say, where's Sam? Sam will be like, yeah, but this isn't statistically significant. Why are you interpreting in this way? That's true. I only have 5 observations here. I cherry picked 5, not cherry pick. I sampled 5 because I wanted to display them visually in that example. But if I run this over the entire data set, all of this will work out just fine. So ignore that for a second. I'm cheating a little bit, but only a little bit. So this would actually work out. Sam seems skeptical. The point is, this is a way of capturing both of those individual level and global level trends in the same model. It's a very clever hack. Okay, we'll be doing this hands-on at the, after presentations shortly. So I'll stop here with this part. Do you have any thoughts or questions or comments on this example in particular? Zoom or room. Okay, so in that case, I would like either Aidan or Courtney to tell us about the 2 papers that we're going to talk about. And I think I can stop sharing and have one of you share instead. Who wants to go first? Do you want to go first, David?
I'm just setting up video.
Okay.
Is the other person ready?
The other person, is Courtney ready?
Wait, what?
Aidan is not ready. He's asking if you might be willing to go first.
Huh. Yeah. Absolutely. Okay.
Thank you. I'm gonna try to mute myself if I can figure out how.
Can you see like my Safari screen right now?
Not yet, but I'm gonna put you up on the screen in just a second. How about now? We can see you on the big screen in the room right now.
Great. Okay, so the paper that I looked at was called Twitter Predicts Citation Rates of Ecological Research. The high-level problem gap hook was that in general, the success of academics, as some of us, might have heard, is often measured through various metrics. But a lot of these traditional metrics like citation count have been criticized for their database dependency. Like, if you look on Google Scholar versus another database, you might get a different count. And there has been increasing popularity in alternative metrics of research impact called alt metrics, very creatively. But the problem is there's very little understanding between the relationship between traditional metrics and these new alt metrics. So the goal of this paper and what they did was they performed a qualitative analysis to quantify the relationship between popular traditional metrics and alt metrics, and to see whether there was one, essentially, and if there was one, what was that relationship. So yeah, to reiterate, their research question, as they put it in the paper, is how does social media activity associated with scientific journal articles translate into more traditional metrics of scholarly output? So the way that they did this was that they had about 1,600 primary research articles, specifically ecology articles, that were published between 2012 and 2014. And they identified various factors that they wanted to study. Specifically, these are the factors that they included in their model. So they looked at the number of tweets, the number of users, the reach of the tweets, the time since publication as a control, and then the number of Web Science citations, which was their response. So before they ran their model, they checked for multicollinearity between all of their explanatory variables. They checked that there was no nonlinear relationship between any of the explanatory variables and the response. And they also standardized the predictor variables to facilitate easier comparison of effect sizes and to ensure maximum likelihood convergence. So the model that they used is, we actually just talked about this in class, and when I was reading it, I was like, ooh, that's quirky. I've never heard of this before. But it's called a generalized linear mixed model. And it is essentially like the generalized linear mixed model. It's kind of fancy. It's an extension of a normal generalized linear model where the predictor contains a random effect in addition to the normal fixed effects, kind of as Bardin just explained like 10 minutes ago. And the random effect in this case, my understanding of it was the journal identity, because they wanted to make sure that, I don't know, they wanted to make sure journal identity wasn't impacting it, or they were trying to control for that. So whatever, they built this model to quantify the relationship between Twitter use and the number of article citations on a specific database. They also, again, as I mentioned, controlled for confounding variables like time since publication, which they have as one of the explanatory variables, and the journal impact factor, which is the random effect in the response. So what they found, that's the wrong direction, sorry. So what they found was that, interestingly, about or over a quarter of the articles didn't even have any corresponding Twitter activity, and another 17% only had like one corresponding tweet. So in general, there were plenty of articles that didn't have any activity at all, which is like interesting. But ultimately, they did actually find that the number of tweets and the time since publication both had positive, statistically significant relationships between them and the number of citations. However, the effect of time since publication was stronger than the effect of number of tweets. One thing that I thought was weird was the way that they discuss identifying statistical significance is pretty much whether their like normal like confidence interval for the coefficient estimates did not include 0, which instead of like saying that they just look at the p-value. And I know that in general, like if your confidence interval does cross 0, you're not going to have a statistically significant p-value, but I didn't realize you could use that as a replacement for p-value, or I don't know if that's just because of the specific model, but that was a specific point that I was kind of confused about and wanted to bring up. And so, yeah, the TLDR is that Twitter activity is associated with, like, it has a positive association with number of future citations. However, that does not mean there's causality. It just means there's an association. And that's it.
I think Yeah,
Sure.
interesting. Thanks. Any thoughts?
I think the confidence interval thing is pretty general. I think that applies to most things where you can look at the confidence interval instead of,
Yes, so I agree with this. They are interchangeable. Actually, the confidence interval approach is probably always preferable to just the approach because you get a much better sense of the range or plausible range for those estimated coefficients. If you just look at the estimated coefficient value and a p-value without looking also at the standard errors, which determine the confidence interval, you only have this sort of middle point. It's so useful to look at the standard errors or the confidence interval because it gives you a better sense of the reasonable range for those estimated coefficients. Even if it's statistically significant, meaning it doesn't cross zero, it's still useful to see what the reasonable range is.
my understanding is that it's only equivalent to the p-value, like the kind of basic standard stuff that we usually do. It's only equivalent if you do a one-sided confidence interval, whereas what you're suggesting, it sounds like you're suggesting you do a two-sided one.
I see.
Which
Okay.
would be like not quite equivalent to the p-value. Like you might not always say that it's statistically significant when it even is because of the p-value. Like you're shifting over here to over here.
I see. Okay. Fair enough. Fair enough. Okay. Yep. Did you hear? Did you? Me?
Yeah, I got that. Thanks.
Okay. What about the work itself and the claim? Is it causal? They control for what kinds of stuff? Could you put up the thing they control for again, Courtney, please?
Yeah, sorry, give me 1 second.
No worries.
So these are the factors.
You have the other desktop on.
Oh, that's so unfortunate.
There.
Okay. So these are the model factors. And then the last one is the response.
Could it be that people who write better papers also tweet more? Luke?
Yeah, I guess my comment regarding this, there's no proper value here. This is not a true experiment. It's
okay.
They're just taking data they've observed in the world, establishing some correlations. So they control for things that they think make might be possible confounding factors. That doesn't mean there could be.
Yep.
Maybe people tweet more if they're more confident.
The one, so I mean, we actually did see a randomized control experiment for tweets. We saw that a few, I don't know, weeks ago when we talked about experiment design. That showed a conclusive, albeit small, effect of tweeting. One thing here that strikes me as odd is, like, I would be cautious of this, inverse relationship between people from more prestigious institutions who maybe write paper more, or I don't know, people that write better papers in general that tweet more. So I think it would have been useful to also control somehow for the quality or prestige of the research groups or things of that nature.
Imagine it's very difficult to control because wouldn't you you're evaluating the metrics, so how would
Metric.
so I guess it's like control for like citation count, like a
For the outcome in citations itself.
yes, that's what I'm thinking.
But the outcome in citations of the particular paper, so you could have a global citation count of the person, maybe, they wouldn't be identical. I agree they'll be correlated perhaps, but still maybe useful to control for.
Yeah.
Okay. The other thing worth mentioning, there was this mention of the term generalized something models. We didn't talk about the class of generalized models just yet. We talked about mixed models a tiny bit just before Courtney's presentation. We didn't talk about generalized at all. We may come back and talk about this at some point. This would include things like logistic regression and negative binomial regression and things of that nature, which we have not yet talked about. But that's just so you know what the term means. Okay, any questions or thoughts more on this? Then I'm going to hand it off to Aidan. Thanks a lot, Courtney. Let's see. Do we have Aidan on the screen? Probably.
You want me to come up?
You can do it from your end. I can mute here. If you can use your mic and camera, that would be good. Audio is off on my end.
Oh, I don't like that. Okay, I don't hear myself. That's good. So this paper is called Evidence for Collective Intelligence Factor in the Performance of Human Groups, by these authors. I really like the first author's last name, Woolley. And don't worry, like not everything is in this font. I just made the title like that because it looks cool. It's the same font as Avatar. So the motivation for this paper is that they think that group performance is just as important as individual performance for different types of cognitive tasks, because in companies or in multiple different scenarios, it's rare that it's actually individuals doing work. And they claim, this seems like a bit of a stretch for me, but they claim that no existing research before that time, 2010, has investigated collective intelligence. And they name this the C factor. And they say that social psychologists have studied group like interacting with each other and how well they do, but not in a statistical way that actually uses that like specific individual tasks to predict future group performance on tasks they haven't seen before. So the way they do it is that they used 699 people working in groups of 2 to 5 and separated them. And I guess they didn't say this, but I guess they're doing it like with it, like not seeing how other people have done it. And so like I can't figure out how many rooms or different locations they put these people in, because obviously it would be cheating if like they're all in the same room. And they are using these tasks from all quadrants of the McGrath task circumplex, which I guess just is like an IQ test, but they somehow made it into a group like puzzle. And so some of these include visual puzzles, different types of brainstorming, or moral judgments. And I guess like some of these can be done by individuals, and we'll see later why that's important. But all of them really makes it so that they try to see if it's easier for a group. And the whole thing with these tasks is it aims to measure collective intelligence, which they say is the inference one draws when the ability of a group to perform one task is significantly correlated with the same group's ability to perform a wide range of other tasks. So I find, like, before I move on, I think that's really weird because they don't specify what that wide range of other tasks means. They just say other tasks. And I feel like if it's really similar tasks, then that's super obvious. Like, of course, if you're really good at one thing and it's other things super similar to it, you're going to be good at it too. But if it's super different, then that seems to be a random thing. But they just don't say. So they have a bunch of these correlation statistics that they just dump out in the paper, where they first say their hypothesis is that a general collective intelligence exists in these groups that goes beyond individual performance. And some of the results I found pretty interesting is the first one is the average inter-item correlation for group scores on different tasks is positive with an R of 0.28, which means that groups that do well on one task generally do well on all of the other tasks. And this is like the average. And so it's the inter-item. So it's like this big matrix where all of the different tasks are put together and the correlation of all of them combined on average is a positive number and it's significant. And so it does seem like their initial hypothesis seems to be true based on this number alone. And second is that the average and maximum intelligence of individual members are not very much correlated with collective intelligence with an R of 0.19, but it is still positive. And so it does seem like having at least one or two really highly intelligent individuals in a group does have some, like a little bit of a positive effect on the group's performance. But then again, like I'm very skeptical of how they measured individual intelligence. But we don't really, like that's not the main point of this paper. And here's like a more detailed table of all of the correlations. And I like that they used both a p-value of 0.05 and 0.001 to show how some of these you can like really reject the null hypothesis. Like you can just, for sure. So some of these are like group matrix reasoning has a 0.86 with a double star. So it seems like matrix reasoning just like if you do well on that one, it seems like you really do well in everything else. And then you can see from like average member intelligence, it like doesn't do much. Like all of the group members individually being kind of smart doesn't prove that the whole group is smart. But somehow maximum seems to be a little bit higher. So that's interesting. So like one person being super, super smart, even though everyone else is dumb, makes the whole group smart. Anyway, does anyone need more time on this? Okay, I'll move on. And I guess this is the most important thing that Bogdan wanted me to talk about is the regression modeling for the test hypothesis. So they basically have this regression coefficient that compares collective intelligence, and you can see from figure 1 to the average and maximum member intelligence, and it just shows that it like is much more significant. You can see the red bar being much higher. And so the conclusion they draw from this is that collective intelligence is a better predictor on group performance than the average and highest intelligence of individual members. And they also use variance to back up their claims. And they do that by having additional similar tasks in total of 10 added on to the original task to show that the variance isn't too large. And so it isn't like by chance that they have these really good correlations with collective performance. And so this graph shows that it is still consistent with their hypothesis, even with the other tasks. I struggled to understand what this figure was really saying, but by the text, I can understand what they're trying to claim. Some of the questions I had while reading this is like, first of all, I liked that they used the regression modeling to show that collective intelligence is a stronger predictor. But I wasn't convinced that individual performance is the only thing you should compare this to. Like, for example, I think that in a group setting, having like the different personalities work together is really important. Like you could have like really, really smart people, but you put them in the same room and they just can't work together. Like, and also like, what about teams with a leader versus teams where everyone is kind of like not leadership material? Or what about just experience? Like some people may have done like these matrix games because they're math PhDs, or they do a lot of machine learning, like all of these experiences versus just what they claim as general intelligence, like IQ test. And more on that is, what about the order of how these teams perform these tasks? So when you say correlation with one task predicting, like with other tasks, well, maybe it's like this one task is really good preparation for the second task. And so when you do this task first, obviously the second task is going to be easier. So I think that, like, because they didn't say that, it makes that correlation claim a bit weaker to me. And that's all I have.
How about now? Yay, okay. So we're talking about the wisdom of the crowds versus this. I think wisdom of the crowds to me sounds more like a regression to the mean effect. Kind of
I don't know enough about it to comment.
so like if I if I ask one of you to estimate my weight, you're probably going to be somewhat off. But if I take the average of all of your estimates of my weight, it's probably going to be really close to what my actual weight is. Sam.
I guess I'm trying to understand what you mean by this. Because to me, regression to the mean is saying like there is some population that we're measuring something that there's a mean population. Measure an outlier of some instance, and then we're like, oh, this is far out. And then we measure again later, some related thing, and find that it's closer. Because in general, we expect the things that we measure are going to be close to the mean.
Yeah.
So when we measure again, we would expect to get closer. But when you say wisdom of the crowds is like the regression to the mean, then like that implies that you already have some expectation that the mean of people's observations is going to be the same as what the actual true thing is, which is like what wisdom of the crowds is saying in the first place, right? So that seems like begging the question.
Yeah, I think the point is that it measures that you're comparing it to like an expert's ability to answer a question, and you wouldn't expect necessarily average people, a group of average people, to be able to answer the question
Okay.
as accurate.
Fair enough. Yeah. Okay. I stand corrected. So that makes sense. But that aside, this idea. So first of all, you know that this came out of CMU, right? You know the first authors, professor here in the business school. We actually talked to her. This is one of the most interesting, I think, ideas that came out of CMU overall, like in general. A very powerful thing. The idea is, just to kind of reiterate on what you were saying, is that when you bring people together in groups, something magical happens, and there's this latent collective intelligence phenomenon or property that emerges when you put people together in a group that cannot be explained by any of the individual level characteristics of the people in that group. Okay, so this level of collective intelligence of the group is not predicted by the average or whatever maximum intelligence of the group members or anything else. It's sort of this this amazing magical thing that emerges that cannot be predicted, or at least not fully, by the individual level characteristics of the people.
I was going to say, kind of like what Aiden is saying last slide. I question whether it's magic or whether it's just a variable that they didn't measure, like personality.
Yeah, they did. Thanks. So that's a good question. They did do a lot more work since then. So go check out their papers. It's all really interesting. For example, group demographic diversity is a good predictor of collective intelligence. And there's other things. So it's interesting. And I guess the other thing about it is that this level of collective intelligence of the group as a whole is more predictive of the group's performance on various tasks than anything else. So that's the other part of this. I think it cannot be explained by individual level factors, and in turn, it explains other things the group does more than the individual level factors. Sort of this, interesting latent property that cannot be directly observed that explains a lot of the variance in performance. I thought it was really interesting. It was sort of fascinating stuff to read.
If you want to point out one thing in this table, the only really big negative number you see that's in a group that's like not individual is the video game one, and it's -10. And so it's like this one group of people, I assume, that's really good at video games, sucks at everything. I think that's really fun. It's not so mean.
Yeah, I wonder, they probably had students, CMU students observed as part of this or something, who play video games maybe.
No, they just are awesome at video games, but then you do moral reasoning, they just suck. I feel like that's the best way to get through these like